Smart pointers. A pointer is a general concept for making for a variable that contains an address in memory. This address refers to or points at some other data. Most common kinds of pointers in Rust. The most common kind of pointer in Rust is a reference, which you learned about in Chapter 4. References are indicated by the AND reference symbol and borrow the value they point to. They don't have any special capabilities other than referencing to data. Also, they don't have any overhead and are the kind of pointer we use most often. Smart pointers, on the other hand, are data structures that not only act like a pointer but also have additional metadata and capabilities. The concept of smart pointers isn't unique to Rust. Smart pointers originated in C++ and exist in other languages as well. In Rust, the different smart pointers defined in the standard library provide functionality beyond that provided by references. One example that we'll explore in this chapter is the reference counting smart pointer type. This pointer enables you to have multiple owners of data by keeping track of the number of owners and, when no owners remain, cleaning up the data. In Rust, which uses the concept of ownership and borrowing, an additional difference between references and smart pointers is the references are pointers that only borrow data. In contrast, in many cases, smart pointers own the data they point to. We've already encountered a few smart pointers in this book, such as strings and vector t in Chapter 8. Although we didn't call them smart pointers at the time, both these types count as smart pointers because they own some memory and allow you to manipulate it. They also have metadata such as their capacity, and extra capabilities or guarantees such as with strings ensuring that data will always be valid UTF-8. Smart pointers are usually implemented using structs. The characteristic that distinguishes a smart pointer from an ordinary struct is that smart pointers implement the deference and drop traits. The defra trait allows an instance of the smart pointer struct to behave like a reference, so you can write code that works with either references or smart pointers. The drop trait allows you to customize the code that is run when an instance of the smart pointer goes out of scope. In this chapter, we'll discuss both traits and demonstrate why they're important to smart pointers. Given that the smart pointer pattern is a general design pattern used frequently in Rust, this chapter won't cover any existing smart pointer. Many libraries have their own smart pointers, and you can even write your own. We'll cover the most common smart pointers in the standard library. Box T for allocating values on a heap, RCT for referencing a reference counting type that enables multiple ownership, reference T and reference mute T access through ref cell T, that type that enforces the borrowing rules at runtime instead of compile time. In addition, we'll cover the intermediate mutability pattern where an immutable type exposes an API for mutating an interior value. We'll also discuss reference cycles, how they can leak memory and how to prevent them. Let's dive in. Using box T to point to data on the heap. The most straightforward smart pointer is a box whose type is written box T. Boxes allow you to store data on the heap rather than the stack. What remains on the stack is the pointer to the heap data. Reference to Chapter 4 to review some the difference between the stack and the heap. Boxes don't have performance overhead other than storing their data on the heap instead of on the stack, but they don't have many extra capabilities either. You use them most often in these situations. When you have a type whose size can't be known at compile time and you want to use a value of that type in a context that requires an exact size. When you have a large amount of data and you want to transfer ownership but ensure that the data won't be copied when you do so. And when you want to own a value and you care only that it's a type that implements a particular trait rather than being of a specific type. We'll demonstrate the first situation in the Enabling Recursive Types with Boxes section. In the second case, transferring ownership of a large amount of data can take a long time because the data is copied around on the stack. To improve performance in this situation, we can store the large amount of data on the heap in a box. Then only the small amount of pointer data is copied around on the stack, while the data it references stays in one place on the heap. The third case is known as trait object, and Chapter 17 devotes an entire section using trait objects that allow for values of different types, just to that topic. So what you've learned here, you'll apply again in Chapter 17. Using a box T to store data on the heap. Before we discuss this use case for box T, we'll cover the syntax and how to interact with values stored within a box T. Listing 15-1 shows how to use a box to store an I32 value on the heap. Listing 15-1, storing an I32 value on the heap using a box. We've defined the variable b to have the value of a box that points to the value 5, which is allocated on the heap. This program will print b equals 5. In this case, we can access the data in the box similar to how we would if the data were on the stack. Just like any owned value, when a box goes out of scope, as B does at the end of main, it will be deallocated. The deallocation happens for the box store on the stack and the data it points to stored on the heap. Putting a single value on the heap isn't very useful, so you won't use boxes by themselves. In this way, very often, having values like a single I32 on the stack where they're stored by default is more appropriate in the majority of situations. Let's look at a case where boxes allow us to define types that we wouldn't be allowed to if we didn't have boxes. Enabling recursive types with boxes. At compile time, Rust needs to know how much space a type takes up. One type whose size can't be known at compile time is a recursive type, where a value can have as part of itself another value of the same type. Because this nesting of values could theoretically continue infinitely, Rust doesn't know how much space a value of a recursive type needs. However, boxes have a known size, so by inserting a box in a recursive type definition, you can have recursive types. Let's explore the cons list, which is a data type common in functional programming languages as an example of a recursive type. The cons list type will define a straightforward except for the recursion. Therefore, the concepts in the example we'll work with will be useful anytime you get into more complex situations involving recursive types. More information about the cons list. The cons list is a data structure that comes from the Lisp programming language and its dialects. In Lisp, the cons function, short for constructive function, constructs a new pair from its two arguments, which usually are a simple value and another pair. These pairs containing pairs form a list. The cons function, construct function concept has made its way into more general function programming jargon. To construct X into Y informally means to construct a new container instance by putting the element X at the start and this new container followed by the container Y. Each item in a construct list contains two elements, the value of the current item and the next item. The last item in the list contains only a value called nil without a next item. A construct list is produced by recursively calling the construct function. The canonical name to denote the base case of recursion is nil. Note that this is not the same as null or nil concept in Chapter 6, which is an invalid or absent value. Although functional programming language uses construct lists frequently, the construct list isn't a commonly used data structure in Rust. Most of the time when you have a list of items in Rust, vector T is a better choice to use. Other, more complex recursive data types are useful in various situations, but by starting with the construct list, we can explore how boxes let us define a recursive data type without much distraction. Listing 15-2 contains an enumeration definition for construct list. Note that this code won't compile yet because the list type doesn't have a known size, which we'll demonstrate. Listing 15-2, the first attempt at defining an enumeration to represent the construct list data structure from I32 values. Note, we're implementing the construct list that holds only I32 values for the purpose of this example. We could have implemented it using generics, as we discussed in Chapter 10, to define a construct list type that could store values of any type. Using the list type to store the list 1, 2, 3 would look like the code in listing 15-3. Listing 15-3 using the list enumeration to store the list 1, 2, 3. The first construct value holds 1, another list value. This list value is another construct value that holds 2, and another list value. This list value is one more construct value that holds 3 and a list value, which is finally nil, the non-recursive variant that signals the end of the list. If we try to compile the code in listing 15-3, we get an error shown in listing 15-4. Listing 15-4, the error we get when attempting to define a recursive enumeration. The error shows this type has infinite size. The reason that we've defined list with a variant that is recursive, it holds another value of itself directly. As a result, Rust can't figure out how much space is needed to store the list value. Let's break down why we get this error a bit. First, let's look at how Rust decides how much space it needs to store a value of a non-recursive type. Computing the size of a non-recursive type. Recall the message enumeration we defined in listing 6-2. We discussed enumeration definitions in chapter 6. To determine how much space to allocate for a message value, Rust goes through each of the variants to see which variant needs the most space. Rust sees that message : quit doesn't need any space. Message : move needs enough space to store 2 I32 values, and so forth. Because only one variant will be used, the most space a message value will need is the space it would take to store the largest of its variants. Contrast this with what happens when Rust tries to determine how much space a recursive type like the list enumeration in listing 15-2 needs. The compiler starts by looking at the constructal variant, which holds a value of type I32 and a value of type list. Therefore, construct needs an amount of space equal to the size of an I32 plus the size of list. To figure out how much memory the list type needs, the compiler looks at the variants. Starting with the constructal variant, the construct variant holds a value of type I32 and a value of list. And this process continues indefinitely as shown in figure 15.1. Figure 15.1, an infinite list consisting of infinite cons variants. Using box T to get a recursive type with a known size. Rust can't figure out how much space to allocate for recursively defined types, so the compiler gives the error in listing 15-4, but the error doesn't include a helpful suggestion. In this suggestion, indirection means that instead of storing a value directly, we'll change the data structure to store the value indirectly by storing a pointer to the value instead. Because a box T is a pointer, Rust always knows how much space a box T needs. A pointer's size doesn't change based on the amount of data it's pointing to. This means we can put a box T inside the construct variant instead of another list value directly. The box T will point to the next list value that will be on the heap rather than inside the construct variant. Conceptually, we still have a list created with lists holding other lists, but this implementation is now more like placing the items next to one another rather than inside one another. We can change the definition of the list enumeration in listing 15-2 and the usage of the list in listing 15-3 to code in listing 15-5, which will compile. Listing 15-5 definition of list that uses box T in order to have a known size. The construct variant will need the size of an I32 plus the space to store the box pointer data. The nil variant stores no values, so it needs less space than a construct variant. We now know that any list value will take up the size of an I32 plus the size of a box pointer data. By using a box, we've broken the infinite recursive chain so that the compiler can figure out the size it needs to store a list value. Figure 15.2 shows what a construct variant looks like now. Figure 15-2, a list that is not indefinitely sized because of construct. A construct holds a box. Boxes provide only the indirection and heap allocation. They don't have any other special capabilities like those we'll see with the other smart pointer types. They also don't have any performance overhead that these special capabilities incur, so they can be useful in cases like the construct list where the indirection is the only feature we need. We'll look at more use cases for boxes in Chapter 17.2. The box T type is a smart pointer because it implements the dereference trait, which allows box T values to be treated like references. When the box T value goes out of scope, the heap data that the box is pointing to is cleaned up as well because of the drop trait implementation. Let's explore these two traits in more detail. These two traits will be even more important to functionality provided by the other smart pointer types we'll discuss in the rest of this chapter. Treating smart pointers like regular references with the dereference trait. Implementing the dereference trait allows you to customize the behavior of the dereference operator, star, as opposed to the multiplication of global operator. By implementing the dereference in such a way that a smart pointer can be treated like a regular reference, you can write code that operates on references and uses that code with smart pointers too. Let's first look at how the dereference operator works with regular references. Then we'll try to define a custom type that behaves like box T and see why the dereference operator doesn't work like a reference on our newly defined type. We'll explore how implementing the dereference trait makes it possible for smart pointers to work in ways similar to references. Then we'll look at Rust Dereference Coercion feature and how it lets us work with either references or smart pointers. Note, there's one big difference between the MyBoxT type we're about to build and the real box T. our version will not store its data on the heap. We are focusing on this example on dereference, so where the data is actually stored is less important than the pointer-like behavior. Following the pointer to the value with the dereference operator. A regular reference is a type of pointer, and one way to think of a pointer is as an arrow to a value stored somewhere else. In listing 15-6, we create a reference to an I32 value and then use the dereference operator to follow the reference to the data. Listing 15-6 using the dereference operator to follow reference to an I32 value. The variable x holds an I32 value 5. We set y equal to the reference to a reference to x. We can assert that x is equal to 5. However, if we want to make an assertion about the value of y, we have to use star y. And let's see, that star is, to get this correct, that star is, it's not on my sheet here. Oh, here it is, asterisk. Okay, well, I guess we're going to call that an asterisk. Okay, we have to use asterisk y to follow the reference to the value it's pointing to, hence dereference. Once we dereference y, we have access to integer value y is pointing to that we can compare with 5. If we tried to write assert underscore eq exclamation point parenthesis 5 comma y parenthesis semicolon, instead we get this compilation error. Comparing a number and a reference to a number isn't allowed because they're different types. We must use the dereference operator to follow the reference to the value it's pointing to. Using box T like a reference. We can write the code in listing 15-6 to use a box T instead of a reference. The dereference operator will work as shown in listing 15-7. Listing 15-7 using the dereference operator on a box I32. The only difference between listing 15-7 and listing 15-6 is that here we set y to be an instance of a box pointing to the value in x rather than a reference pointing to the value of x. In the last assertion, we can use the dereference operator to follow the box pointer in the same way that we did when y was a reference. Next, we'll explore what is special about box T that enables us to use the dereference operator by defining our own box type. Defining our own smart pointer. Let's build a smart pointer similar to the box T type provided by the standard library to experience how smart pointers behave differently from references by default. Then we'll look at how to add the ability to use the dereference operator. The box T type is ultimately defined as a tuple struct with one element, so listing 15-8 defines a myBoxT type in the same way. We'll also define a new function to match the new function defined on box T. Listing 15-8 defining a myBoxT type. We define a struct named myBox and declare a generic parameter t. Because we want our type to hold values of any type, the myBox type is a tuple struct with one element of type t. The myBox : new function takes one parameter of type t and returns a myBox instance that holds the value passed in. Let's try adding the main function in listing 15-7 to listing 15-8 and changing it to use myBoxT type we've defined instead of box T. The code in listing 15-9 won't compile because Rust doesn't know how to dereference myBox. Listing 15-9 attempting to use myBoxT in the same way we used references and box T. Here's the resulting compilation error. Our myBoxT type can't be dereferenced because we haven't implemented that ability on our type. To enable dereferencing with the what did I call that? Asterisk. Dereferencing with the asterisk operator, we implement the dereference trait, treating a type like a reference by implementing the dereference trait. As discussed in Chapter 10, to implement a trait we need to provide implementations for the trait's required methods. The dereference trait provided by the standard library requires us to implement one method named dereference that borrows self and returns a reference to the inner data. Listing 15-10 contains an implementation of dereference to add to the definition of myBox. Listing 15-10 implementing dereference on myBoxT. The type target equals t, semicolon, semicolon. Syntax defines an associated type for the dereference trait to use. Associated types are a slightly different way of declaring a generic parameter. But you don't need to worry about them for now. We'll cover them in more detail in Chapter 19. We fill in the body of the dereference method with reference self.0, so dereference returns a reference to the value we want to access with the asterisk operator. The main function in the listing 15-9 that calls asterisk on the myBoxT value now compiles and the assertions pass. Without the dereference trait, the compiler can only dereference references. The dereference method gives the compiler the ability to take the value of any type that implements dereference and call the dereference method to get a reference that it knows how to dereference. Then we enter asterisk y in listing 15-9 behind the scenes. Rust actually ran this code. Rust substitutes the asterisk operator with a call to the dereference method and then a plain dereference, so we don't have to think about whether or not we need to call the dereference method. This Rust feature lets us write code that functions identically whether we have a regular reference or a type that implements dereference. The reason the dereference method returns a reference to a value and that the plain dereference outside the parentheses in asterisk parenthesis y dot dereference and a bunch more of the parentheses is still necessary. This, let's see, is the ownership system is necessary, is the ownership system. If the dereference method returned a value directly instead of a reference to a value, the value would be moved out of self. We don't want to take ownership of the inner value inside my box T. In this case, or in most cases, where we use the dereference operator. Note that the asterisk operator is replaced with a call to dereference method and then a call to the asterisk operator just once. Each time we use a asterisk in our code, because the substitution of the asterisk operator does not recurse infinitely, we end up with data of type I32, which matches the 5 in assert underscore equal EQ exclamation mark in listing 15-9. Implicit dereference coercions with functions and methods. Dereference coercion is a convenience that Rust performs on arguments to functions and methods. Dereference coercion converts a reference to a type that implements dereference into a reference to a type that dereference can convert the original type into. Dereference coercion happens automatically when we pass a reference to a particular type's value as an argument to the function or method that doesn't match the parameter type in the function or method definition. A sequence of calls to the dereference method converts the type we provided into the type the parameter needs. Dereference coercion was added to Rust so that programmers writing function and method calls don't need to add as many explicit references and dereferences with reference and asterisk. The dereference coercion feature also lets us write more code that can work for either reference or smart pointers. To see dereference coercion in action, let's use the myBoxT. Type we defined in listing 15-8, as well as the implementation of dereference that we added in listing 15-10. Listing 15-11 shows the definition of a function that has a string slice parameter. Listing 15-11, a hello function that has a parameter name of type reference string. We can call the hello function with a string slice as an argument, such as hello parenthesis double quote Rust double quote parenthesis semicolon. For example, dereference coercion makes it possible to call hello with a reference to a value of type myBox less than sign string greater than sign, as shown in listing 15-12. Listing 15-12 calling hello with a reference to a myBox string value, which works because of dereference coercion. Here we're calling the hello function with the argument reference m, which is a reference to a myBox string value because we implemented the dereference trait on myBoxT. In listing 15-10, Rust can turn reference myBox string into reference string by calling dereference. The standard library provides an implementation of dereference on string that returns a string slice, and this is in the API documentation for dereference. Rust calls dereference again to turn the reference string into reference str, which matches the hello function's definition. If Rust didn't implement dereference coercion, we would have to write the code in listing 15-13 instead of the code in listing 15-12 to call hello with a value type reference mybox string. Listing 15-13, the code we would have to write if Rust didn't have dereference coercion. The *M dereferences the mybox string into a string, and then reference and period take a string slice of the string that is equal to the whole string to match the signature of hello. The code without dereference coercion is harder to read, write, and understand with all of these symbols involved. Dereference coercion allows Rust to handle these conversions for us automatically. When the dereference trait is defined for the types involved, Rust will analyze the types and use dereference : okay, is that a... I'm just going to look that up real quick. Yep, : dereference as many times as necessary to get the reference to match the parameter's type. The number of times that dereference : dereference needs to be inserted is resolved at compile time, so there is no runtime penalty for taking advantage of dereference coercion. How dereference coercion interacts with mutability. Similar to how you use dereference trait to override the asterisk operator on immutable references, you can use the dereference mute trait to override the asterisk operator on mutable references. Rust does dereference coercion when it finds types and traits implemented in 3 cases: from reference T to reference U when T : dereference F target equals U, from reference mute T to reference mute U when T : dereference mute target equal U, from reference mute T to reference U when T : T : dereference less than target equals U. Okay, the first 2 cases are the same except for mutability. The first case states that if you have a reference T and a T implements dereference to some type U, you can get a reference U transparently. The second case states that the same dereference coercion happens for immutable references. The third case is trickier. Rust will also coerce a mutable reference to an immutable one, but the reverse is not possible. Immutable references will never coerce to mutable references because of the borrowing rule. If you have a mutable reference, that mutable reference must be the only reference to the data. Otherwise, the program wouldn't compile. Converting one mutable reference to one immutable reference will never break the borrowing rules. Converting an immutable reference to a mutable reference would require that there is only one immutable reference to the data, and the borrowing rules don't guarantee that. Therefore, Rust can't make the assumption that converting an immutable reference to a mutable reference is possible. Running code on cleanup with the drop trait. The second trait important to the smart pointer pattern is drop, which lets you customize what happens when a value is about to go out of scope. You can provide an implementation for the drop trait on any type, and the code you specify can be used to release resources like files or network connections. We're introducing drop in the context of smart pointers because the functionality of drop trait is almost always used when implementing a smart pointer. For example, box T customizes drop to deallocate the space on the heap that the box points to. In some languages, the programmer must call code to free memory or resources every time they finish using an instance of a smart pointer. If they forget, the system might become overloaded and crash. In Rust, you can specify that a particular bit of code be run whenever a value goes out of scope, and the compiler will insert the code automatically. As a result, you don't need to be careful about placing cleanup code everywhere in a program that an instance of a particular type is finished with. You still won't leak resources. Specifically, the code to run when a value goes out of scope by implementing the drop trait. The drop trait requires you to implement one method named drop that takes a mutable reference to self. To see when Rust calls drop, let's implement drop with print line exclamation mark statements for now. Listing 15-14 shows a custom smart pointer struct whose only custom functionality is that it will print dropping custom smart pointer exclamation mark when the instance goes out of scope. This example demonstrates when Rust runs the drop function. Listing 15-14, a custom smart pointer struct that implements the drop trait where we would put our cleanup code. The drop trait is included in the prelude, so we don't need to bring it into scope. We implement the drop trait on custom smart pointer and provide an implementation for drop method that calls print line exclamation mark. The body of the drop function is where you would place any logic that you want to run when an instance of your type goes out of scope. We're printing some text here to demonstrate when Rust will call drop. In main, we create two instances of custom smart pointer and then print custom smart pointers created. At the end of main, our instance of custom smart pointer will go out of scope and Rust will call the code when we put it in drop method, printing our final message. Note that we didn't need to call the drop method explicitly. When we run this program, we'll see the following output. Rust automatically called drop for us when our instances went out of scope. Calling the code we specified, variables are dropped in the reverse order of their conditions, so D was dropped before C. This example gives you a visual guide to how the drop method works. Usually you would specify the cleanup code that your type needs to run rather than print message. Dropping a value early with standard library memory drop. Guessing MEM stands for memory. Unfortunately, it's not straightforward to disable the automatic drop functionality. Disabling drop isn't usually necessary. The whole point of the drop trait is that it's taken care of automatically. Occasionally, however, you might want to clean up a value early. One example is when using smart pointers that manage locks. You might want to force the drop method that releases the lock so that other code in the same scope can acquire the lock. Rust doesn't let you call the drops trait drop method manually. Instead, you have to call the standard library memory drop function provided by the standard library if you want to force a value to be dropped before the end of scope. If we try to call drop traits drop method manually by modifying the main function from listing 15-14 as shown in listing 15-15, we'll get a compiler error. Listing 15-15 attempting to call the drop method from a drop trait manually to clean up early. When we try to compile this code, we'll get an error. We'll get this error. This error message states that we're not allowed to explicitly call drop. The error message uses a term destructor, which is the general programming term for a function that cleans up an instance. A destructor is analogous to a constructor which creates an instance. The drop function in Rust is one particular destructor. Rust doesn't let us call drop explicitly because Rust would still automatically drop the value at the end of main. This would be a double free error because Rust would be trying to clean up the same code twice, same value twice. We can disable the automatic insertion of drop when the value goes out of scope. We can't call the drop method explicitly. So if we need to force a value to be cleaned up early, we can use the standard library memory drop function. The standard library memory drop function is different from the drop method in the drop trait. We call it by passing the value we want to force it to be dropped early as an argument. The function is in prelude, so we can modify main in listing 15-15 to call the drop function as shown in listing 15-16. Listing 15-16 calling standard library memory drop to explicitly drop a value before it goes out of scope. Running this code will print the following. The text dropping custom smart pointer with data some data exclamation mark is printed between the custom smart pointer created and custom smart pointer drop before the end of main. Text showing that the drop method is called to drop C at that point. You can use code specified in a drop trait implementation in many ways to make cleanup convenient and safe. For instance, you could use the create your own memory allocator with the drop trait and Rust's ownership system. You don't have to remember to clean up because Rust does it automatically. You also don't have to worry about problems resulting from accidentally cleaning up values still in use. The ownership system that makes sure references are always valid also ensures that drop gets called only once when the value is no longer being used. Now that we've examined box T and some of the characteristics of smart pointers, let's look at a few other smart pointers defined in the standard library. RCT, the reference counted smart pointer. In the majority of cases, ownership is clear. You know exactly which variable owns a given value. However, there are cases when a single value might have multiple owners. For example, in graph data structures, multiple edges might point to the same node. And that node is conceptually owned by all of the edges that point to it. A node shouldn't be cleaned up unless it doesn't have any edges pointing to it. To enable multiple ownership, Rust has a type called RCT, which is an abbreviation for reference counting. The reference counting T type keeps track of the number of references to a value, which determines whether or not a value is still in use. If there are 0 references to value, the value can be cleaned up without any references becoming invalid. Imagine, imagine reference counting T as a TV in a family room. When one person enters to watch a TV, they turn it on. Others can come into the room and watch the TV. When the last person leaves the room, they turn off the TV because it's no longer being used. If, where was I? If someone turns off the TV while others are still watching it, there would be an uproar from the remaining TV watchers. We use the reference counting T type when we want to allocate some data on a heap for multiple parts of our program to read, and we can't determine at compile time which part will finish using the data last. If we knew which part would finish last, we could just make that part of the data's owner, and the normal ownership rules enforced at compile time would take effect. Note that reference counting T is only used in single thread scenarios. When we discuss concurrency in Chapter 16, we'll cover how to do reference counting in multiple thread programs. Using reference counting T to share data. Let's return to our cons list example in listing 15-5. Recall that we defined it using box T. This time we'll create 2 lists that both share ownership of a third list. Conceptually, this looks similar to figure 15.3. Figure 15-3, 2 lists B and C sharing ownership of the third list A. Okay, RC, we need to keep that in mind, that is reference counting. We'll create a list A that contains 5 and then 10. We'll make 2 more lists B that start with 3 and C that starts with 4. Both B and C lists will then continue to the first A list containing 5 and 10. In other words, both lists will share the first list containing 5 and 10. Try to implement this scenario using our definitions list with box T. Won't work, as shown in listing 15-17. Listing 15-17, demonstrating we're not allowed to have 2 lists under box T. That'll try to share ownership of a third list. When we compile this code, we get this error. The cons variant owned the data they hold. So when we create the B list, A is moved into B and B owns A. Then we tried to use A again when creating C. We're not allowed to because A has been moved. We could change the definition of cons to hold references instead, but then we would have to specify lifetime parameters. By specifying lifetime parameters, we would be specifying that every element in the list will live at least as long as the entire list. The borrow checker wouldn't let us compile. Let A equal cons 10 reference nil. For example, because the temporary nil value would be dropped before A could take a reference to it. Instead, we'll change our definition of a list to use reference counting T to place in place of box T as shown in listing 15-18. Each cons variant will now hold a value and an reference counting T pointing to a list. When we create B, instead of taking ownership of A, we'll clone the reference counting list that A is holding, thereby increasing the number of references from 1 to 2 and letting A and B share ownership of the data in that reference counting list. We'll also clone A when creating C, increasing the number of references from 2 to 3 every time we call reference counting : clone. The reference count to the data within the reference count list will increase, and the data won't be cleaned up unless there are 0 references to it. Listing 15-18, a definition of list that uses reference count T. We need to add a use statement to bring reference count T into scope because it's not in the prelude. In main, we create the list holding 5 and 10 and store it in a new reference count list in A. Then we create B and C. We call the reference clone function to pass a reference to the reference. Now, what did I call that again? Reference what? Okay, well, we're just going to continue on, and I'm just going to use RC. Reference count, I'm sorry. Listing 15-18, a definition of a list that uses reference count T. We need to add use statement to bring reference count T into scope because it's not in the prelude. In main, we create the list holding 5 and 10 and store it in a new reference count list. In A, then we create B and C. We call the reference, there I go again, reference count clone function and pass the reference to the reference count list in A as an argument. We could have called A period clone, and that is parentheses, rather than reference count clone parentheses reference A, but Rust's convention is to use reference count clone in this case. The implementation of reference count clone doesn't make a deep copy of the data like most types. Implementations of clone do. The call to reference count clone only increments the reference count, which doesn't take much time. Deep copies of data can take a lot of time. By using reference count clone for referencing counting, we can visually distinguish between the deep copy kinds of clones and the kinds of clones that increase the reference count. When looking at performance problems in the code, we only need to consider the deep copy clones and can disregard calls to reference count clone. Cloning and reference count T increases the reference count. Let's change our working example in listing 15-18 so that we can see the reference counts changing as we create and drop references to the reference count list in A. In listing 15-19, we'll change main so that it has an inner scope around list C. Then we can see how the reference count changes when C goes out of scope. Listing 15-19, printing the reference count. At each point in the program where the reference count changes, we print the reference count, which we can get by calling the reference count : strong underscore count function. This function is named strong underscore count rather than count because the reference count T type also has a weak underscore count. We'll see that weak underscore count is used in the preventing references cycles, turning an reference count T into a weak T section. This count prints the following. We can see that reference count list in A has an initial count reference count of 1. Then each time we call clone, the count goes up by 1. When C goes out of scope, the count goes down by 1. We don't have to call a function to decrease the reference count like we have to call reference count : clone to increase the reference count. The implementation of drop trait decreases the reference count automatically when the reference count T value goes out of scope. What we can't see in this example is that when B and then A go out of scope at the end of main, the count is 0 and the reference count list is cleaned up completely at that point. Using reference count T allows a single value to have multiple owners, and the count ensures that the value remains valid as long as any of the owners still exist. Via immutable references, reference count T allows you to share data between multiple parts of your program for reading only. If reference count T allowed you to have multiple mutable references too, you might violate one of the borrowing rules discussed in Chapter 4. Multiple mutable borrows to the same place can cause data races and inconsistencies, but being able to mute data is very useful. In the next section, we'll discuss interior mutability pattern and the reference cell T type that you can use in conjunction with reference count T to work with this immutability restriction. Reference cell T and the interior mutability pattern. Internal mutability is a design pattern in Rust that allows you to mutate data even when there are immutable references to that data. Normally, this action is disallowed by the borrowing rules. To mutate data, the pattern uses unsafe code inside a data structure to bend Rust's usual rules that govern mutation and borrowing. We haven't yet covered unsafe code. We will in Chapter 19. We can use types that use the interior mutability pattern when we can ensure that the borrowing rules will be followed at runtime. Even though the compiler can't guarantee that, the unsafe code involved is then wrapped in a safe API and the outer type is still immutable. Let's explore this concept by looking at the reference cell T type that follows the interior mutability pattern. enforcing borrowing rules at runtime with reference cell T. Like reference count T, the reference cell T type represents single ownership over the data it holds. So what makes reference cell T different from the type like box T? Recall the borrowing rules you learned in Chapter 4. At any given time, you can have either, but not both of, one mutable reference or any number of immutable references. References must always be valid. With references and box T, the borrowing rules variants are enforced at compile time with reference cell T. These variants are enforced at runtime with references. If you break these rules, you'll get a compiler error. With reference cell T, if you break these rules, your program will panic and exit. The advantages of checking the borrowing rules at compile time are that errors will be caught sooner in the development process, and there is no impact on runtime performance because all of the analysis is completed beforehand. For those reasons, checking the borrowing rules at compile time is the best choice in the majority of cases, which is why this is Rust's default. The advantage of checking the borrowing rules at runtime instead is that certain memory-safe scenarios are then allowed, whereas they are disallowed by the compile time checks. Static analysis like the Rust compiler is inherently conservative. Some properties of code are impossible to detect by analyzing the code. The most famous example is the halting problem, which is beyond the scope of this book but is an interesting topic to research. Because some analysis is impossible, if the Rust compiler can't be sure the code compiles with the ownership rules, it might reject a correct program. In this way, it's conservative. If Rust accepts an incorrect program, users wouldn't be able to trust in the guarantees Rust makes. However, if Rust rejects a correct program, the programmer will be inconvenienced, but nothing catastrophic can occur. The reference cell T type is useful when you're sure your code follows the borrowing rules, but the compiler is unable to understand that guarantee that. Similar to reference count T, reference cell T is only used in single thread scenarios, and you will give a and will give you a compile time error if you try using it in a multi-thread context. We'll talk about how to get the functionality of reference CT, reference cell T, in a multi-thread program in Chapter 16. Here's a recap of the reasons to choose box T, reference count T, or reference cell T. Reference count T enables multiple owners of the same data, box T, and reference cell T to have single owners. Box T allows immutable and mutable borrows checked at compile time. Reference count T allows only immutable borrows checked at compile time. Reference cell T allows immutable or mutable borrows checked at runtime. Because reference cell T allows mutable borrows checked at runtime, you can mutate the value inside the reference cell T, even when the reference cell T is immutable. Mutating the value inside an immutable value is the interior mutability pattern. Let's look at a situation in which interior mutability is used and examine how it's possible. Interior mutability and mutable borrow to an immutable value. A consequence of the borrowing rules is that when you have an immutable value, you can't borrow it mutably. For example, this code won't compile. If you tried to compile this code, you'd get the following error. However, there are situations in which it would be useful for a value to mutate itself in its methods, but appear immutable to other code. Code outside the values methods would not be able to mutate the value. Using reference cell T is one way to get that ability to have interior mutability, but reference cell T doesn't get around the borrowing rules completely. The borrow checker at compiler in the compiler allows this interior mutability, and the borrowing rules are checked at runtime instead. If you violate the rules, you'll get a panic instead of a compiler error. Let's work through a practical example where we can use reference cell T to mutate an immutable value and see why that is useful. A use case for interior mutability mock objects. A test double is the general programming concept for a type used in place of another type during testing. Mock objects are specific types of test doubles that record what's happening during a test so you can assert that correct actions took place. Rust doesn't have objects in the same sense as other languages have objects, and Rust doesn't have mock object functionality built into the standard library as some other languages do. However, you can definitely create a struct that will serve the same purpose as a mock object. Here's the scenario we'll test. We'll create a library that tracks a value against a maximum value and sends messages based on how close to the maximum value the current value is. This library could be used to keep track of a user's quota for the number of API calls they're allowed to make, for example. Our library will only provide the functionality of tracking how close to the maximum a value is and what the messages should be at what times. Applications that use our library will be expected to provide the mechanism for sending the messages. The application could put any message in the application, send an email, send a text message, or something. The library doesn't need to know that detail. All it needs is something that implements a trait we'll provide called messenger. Listing 15-20 shows the library code. Listing 15-20, a library to track how close a value is to maximum value and warn when the value is at certain levels. One important part of this code is that the messenger trait has one method call, send, that takes an immutable reference to self and the text of the message. This is the interface our mock object needs to have. The other important part is that we want to test the behavior of the set_value method on the limit tracker. We can change what passes in for the value parameter, but set_value doesn't return anything for us to make assertions on. We want to be able to say that if we create a limit tracker with something that implements the messenger trait and a particular value for max, when we pass different numbers for value, the messenger is told to send the appropriate message. We need a mock object that, instead of sending an email or text message when we call send, will only keep track of the messages it's told to send. We can create a new instance of the mock object, create a limit tracker that uses the mock object, call the set underscore value method on the limit tracker, and then check that the mock object has the messages we expect. Listing 15-21 shows an attempt to implement a mock object to do just that, but the borrow checker won't allow it. Listing 15-21 an attempt to implement a mock messenger that isn't allowed by the borrow checker. This test code defines a mock messenger struct that has a sent underscore messages field with the vector of string values to keep track of the messages it's told to send. We also define an associated function new to make it convenient to create a new mock messenger values that start with an empty list of messages. We then implement the messenger trait of mock messenger so that we can give a mock messenger to a limit tracker. In the definition of the send method, we take the message passed in as a parameter and store it in the mock messenger list of sent underscore messages. In the test, we're testing what happens when the limit tracker is told to set value to something that is more than 75% of the max value. First, we create a new mock messenger, which we will start with an empty list of messages. Then we create a new limit tracker and give it a reference to the new mock messenger and a maximum value of 100. We call the set underscore value method on the limit tracker with a value of 80, which is more than 75% of 100. Then we assert that the list of messages that the mock messenger is keeping track of should now have one message in it. However, there's a problem with this test as shown here. We can't modify the mock messenger to keep track of messages because the sent method takes an immutable reference to self. We also can't take the suggestion from the error text to use reference mute self instead, because then the signature of send wouldn't match the signature in the messenger trait definition. Feel free to try and see what error message you get. This is a situation in which interior mutability can help. We'll store the sent underscore messages with a reference LT, and then the send message will be able to modify sent underscore messages to store the messages we've seen. Listing 15-22 shows what that looks like. Listing 15-22 using a reference cell T to mutate an inner value while the outer value is considered immutable. The sent underscore messages field is now of type reference cell vector string instead of vector string. In the new function, we create a new reference cell vector string instance around the empty vector. For the implementation of the send method, the first parameter is still an immutable borrow of self, which matches the trait definition. We call borrow underscore mute on the reference cell vector string in the self.sent underscore message to get a mutable reference to the value inside the reference cell vector string, which is the vector. Then we can call push on the mutable reference to the vector to keep track of the messages sent during the test. The last change we have to make is in the assertion. To see how many items are in the inner vector, we call borrow on the reference cell vector string to get an immutable reference to the vector. Now that you've seen how to use reference cell T, let's dig into how it works. keeping track of borrows at runtime with reference cell T. When creating immutable and mutable references, we use the reference and reference mute syntax respectively. With reference cell T, we use the borrow and borrow underscore mute methods, which are part of the safe API that belong to reference cell T. The borrow method returns the smart pointer type reference T, and borrow underscore mute returns the smart pointer type reference mute T. Both types implement dereference, so we can treat them like regular references. The reference cell T keeps track of how many reference T and reference mute T smart pointers are currently active. Every time we call borrow, the reference cell T increases its count of how many immutable borrows are active. When the reference T value goes out of scope, the count of immutable borrows goes down by 1. Just like the compiler time borrowing rules, reference cell T lets us have many immutable borrows or one mutable borrow at any point in time. If we try to violate these rules rather than getting a compiler error, as we would with references, the implementation of reference cell T will panic at runtime. Listing 15-23 shows a modification of the implementation of send. In listing 15-22, we're deliberately trying to create two mutable borrows active for the same scope to illustrate that reference cell T prevents us from doing this at runtime. Listing 15-23, creating two mutable references at the same scope to see that reference cell T will panic. We created a variable, one underscore borrow, for the reference mute T. Smart pointer returned from the borrow underscore mute. Then we create another mutable borrow in the same way in the variable to underscore borrow. This makes two mutable references in the same scope, which isn't allowed. Then we run the tests for our library. The code in listing 15-23 will compile without any errors, but the test will fail. Notice that the code panicked with the message already borrowed, borrow mute error. This is how reference T handles violations of the borrowing rules at runtime. Catching borrowing errors at runtime rather than compile time means that you would find a mistake in your code later in the development process, and possibly not until your code was deployed to production. Also, your code would incur a small runtime performance penalty as a result of keeping track of the borrows at runtime rather than compile time. However, using reference cell T makes it possible to write a mock object that can modify itself to keep track of those messages it has seen while you're using it in a context where only immutable values are allowed. You can use reference cell T despite its trade-offs to get more functionality than regular references provide. Having multiple owners of mutable data by containing reference count T and reference cell T. A common way to use reference cell T is in combination with reference count T. Recall that reference count T lets you have multiple owners of the same data, but it only gives immutable access to that data. If you have a reference count T that holds a reference cell T, you can get a value that can have multiple owners and that you can mutate. For example, recall the cons list example in 15-18 where we use reference count T to allow a mutable list to share ownership of another list. Because reference count T holds only immutable values, we can't change any of the values in the list once we've created them. Let's add the reference cell T to gain the ability to change the values in the list. Listing 15-24 shows that by using the reference cell T in the cons definition, we can modify the values stored in all the lists. Listing 15-24 using reference count, reference cell I32 to create a list that we can mutate. So, we create a value that is an instance of reference count, reference cell I32 and stored in a variable named value, so we can access it directly later. Then we create a list in A with the cons variant that holds value. We need to clone value so both A and value have ownership of the inner 5 value rather than transferring ownership from value to A or having A borrow from value. We wrap the list A in an reference count T, so when we create lists B and C, they can both refer to A, which is what we did in listing 15-18. After we've created the lists in A, B, and C, we add 10 to the value in value. We do this by calling borrow_mute on value, which uses the automatic dereferencing feature we discussed in Chapter 5. See the section where the arrow operator ? To dereference the reference count T to the inner reference cell T value, the borrow_mute method returns a reference mute T smart pointer, and we use the dereference operator on it and change the inner value. When we print A, B, and C, we can see that they all have the modified value of 15 rather than 5. This technique is pretty neat. By using reference cell T, we have an outwardly immutable list value, but we can use the methods on reference cell T that provides access to its interior mutability so we can modify our data when we need to. The runtime checks of the borrowing rules protect us from data races, and it's something worth trading a bit of speed for this flexibility in our data structures. The standard library has other types that provide interior mutability, such as cell T, which is similar except that instead of giving reference to the inner value, the value is copied in and out of the cell T. There's also mute XT, which offers interior mutability that's safe to use across threads. We'll discuss its use in Chapter 16. Check out the standard library docs for more details on the differences between these types. Reference cycles that can leak memory. Rust memory safety guarantee makes it difficult but not impossible to accidentally create memory that is never cleaned up, known as a memory leak. Preventing memory leaks entirely is not one of Rust's guarantees in the same way that disallowing data races at compile time is, meaning memory leaks are memory safe in Rust. We can see that Rust allows memory leaks by using reference count T and reference cell T. It's possible to create references where items refer to each other in a cycle. This creates memory leaks because the reference count of each item in the cycle will never reach 0, and the values will never be dropped. Creating a reference cycle. Let's look at how a reference cycle might happen and how to prevent it, starting with the definition of the list enumeration and a tail method in listing 15-25. Listing 15-25, a cons list definition that holds a reference cell T so that we can modify what a cons variant is referring to. We are using another variation of the list definition from 15-5. The second element in the cons variant is now reference cell, reference count list, meaning that instead of having the ability to modify the I32 value as we did in listing 15-24, we want to modify which list value a const variant is pointing to. We're also adding a tail method to make it convenient for us to access the second item if we have a cons variant. In listing 15-26, we're adding a main function that uses the definitions in listing 15-25. This code creates a list in A and a list in B that points to the list in A, then modifies the list in A to point to B, creating a reference cycle. There are print line exclamation mark statements along the way to show what the reference counts at the various points in the process. Listing 15-26, creating a reference cycle of two list values pointing to each other. We create an reference count list instance holding a list value in the variable A with an initial list of 5, nil. We then create a reference count list instance holding another list value in the variable B that contains the value and points to the list in A. We modify A so it points to B instead of nil, creating a cycle. We do that by using the tail method to get a reference to the reference cell reference count list in A, which we put in the variable link. Then we use the borrow_mute method on the reference cell reference count list to change the value inside an reference count list that holds a nil value to the reference count list in B. When we run this code, keeping the last print line exclamation mark commented out for the moment, we will get this output. The reference count of the reference count lists insists in both A and B are 2 after we change the list in A to point to B. At the end of main, Rust will try to drop B first, which will decrease the count of reference count list instance in B by 1. However, because A is still referencing the reference count list that was in B, that reference count list has a count of 1 rather than 0. So the memory in reference count list has on the heap won't be dropped. The memory will just sit there with a count of 1 forever. To visualize this reference cycle, we've created a diagram in figure 15.4. Figure 15.4, a reference cycle of lists A and B pointing to each other. If you uncomment the last print line exclamation mark and run the program, Rust will try to print this cycle with a pointing to B, pointing to A, and so forth until it overflows the stack. In this case, right after we create the reference cycle, the program ends. The consequences of this cycle aren't very dire. However, a more complex program allocated lots of memory in a cycle and held into it for a long time, the program would use more memory than it needed and might overwhelm the system, causing it to run out of available memory. Creating reference cycles is not easily done, but it's not impossible either. If you have a reference cell T value that contains reference count T, values are similar nested combinations of types with interior mutability and reference counting, you must ensure that you don't create cycles. You can't rely on Rust to catch them. Creating a reference cycle would be a logic bug in your program that you should automate tests. Use automated tests, code reviews, and other software development practices to minimize. Another solution for avoiding reference cycles is reorganizing your data structures so that some references express ownership and some references don't. As a result, you will have cycles made up of some ownership relationships and some non-ownership relationships, and only the ownership relationships affect whether or not a value can be dropped. In listing 15-25, we always want cons variant to own their list. So reorganizing the data structure isn't impossible. Let's look at an example using graphs made up of the parent node and the child nodes to see when non-ownership relationships are an appropriate way to prevent reference cycles. Preventing reference cycles, turning a reference count T into a weak T. So far we've demonstrated that calling reference count : clone increases the strong underscore count of an reference count T instance, and an reference count T instance is only cleaned up if its strong underscore count is 0. You can also create a weak reference to the value within an reference count T instance by calling reference count : downgrade and passing a reference to the reference count T. When you call RC reference count : downgrade, you get a smart pointer with type weak T instead of increasing the strong underscore count in the reference count T instance by calling reference count : downgrade increases the weak underscore count by 1. The reference count T type uses weak underscore count to keep track of how many weak T references exist, similar to strong underscore count. The difference is weak underscore count doesn't need to be 0 for the reference count T instance to be cleaned up. Strong references are how you can share ownership of an reference count T instance. Weak references don't express an ownership relationship. They won't cause a reference cycle because any cycle involving some weak references will be broken once the strong reference count of values involved is 0. Because the value that weak T references might have been dropped, to do anything with the value that a weak T is pointing to, you must make sure the value still exists. Do this by calling the upgrade method on a weak T instance, which will return an option reference count T. You'll get a result of sum if the reference count T value has not been dropped yet and a result of none if the reference count T value has been dropped. Because upgrade returns an option T, Rust will ensure that the sum case and the none case are handled, and there won't be an invalid pointer. An example, as an example, rather than using a list whose items know only about the next item, will create a tree whose items know about their children items and their parent items. Creating a tree data structure, a node with child nodes. To start, we'll build a tree with nodes that know about their child nodes. We'll create a struct named node that holds its own I32 value as well as reference to its child's node values. We want a node to own its children, and we want to share that ownership with variables so that we can access node in the tree directly. To do this, we define the vector t item to be values of type reference count node. We also want to modify which nodes are children of another node. So we have a reference cell t in children around the vector reference count node. Next, we'll use our struct definitions to create one node instance named leaf with the value 3 and no children, and another instance named branch with the value 5 and leaf as one of its children, as shown in listing 15-27. Listing 15-27, creating a leaf node with no children and a branch node with leaf as one of its children. We clone the reference count node in leaf and store that in branch, meaning the node in leaf now has two owners, leaf and branch. We can get from branch to leaf through branch.children, but there's no way to get from leaf to branch. Okay, the reason is leaf has no reference to branch and doesn't know they're related. We want leaf to know that branch is its parent. We'll do that next. Adding a reference from a child to its parent. To make the child node aware of its parent, we need to add a parent field to our node struct definition. The trouble is in deciding what type of parent should be. We know it can't contain reference count t because that would create a reference cycle with leaf.parent pointing to branch and branch.children pointing to leaf, which would cause their strong underscore count values to never be 0. Thinking about the relationship another way, a parent node should own its children. If a parent node is dropped, its child node should be dropped as well. However, a child should not own its parent. If we drop the child node, the parent should still exist. This is a case for weak references. So instead of reference count t, we'll make the type of parent use weak t, specifically a reference cell weak node. Now our node struct definition looks like this. A node will be able to refer to its parent node but doesn't own its parent. In listing 15-28, we update main to use this new definition, so the leaf node will have a way to refer to its parent branch. Listing 15-28, a leaf node with a weak reference to its parent node branch. Creating the leaf node looks similar to how creating the leaf node looked in listing 15-27 with the exception of the parent field. Leaf starts out with out a parent, so we create a new empty weak node reference instance. At this point, we try to get a reference to the parent of leaf by using the upgrade method. We get a none value. We see this is in the output from the first print line exclamation mark statement. When we create the branch node, it will also have a new weak node reference in the parent field. Because the branch doesn't have a parent node, we still have leaf as one of the children of branch. Once we have the node instance in branch, we can modify leaf to give it a weak node reference to its parent. We use the borrow underscore mute method on the reference cell weak node in the parent field of leaf, and then we use the reference count : downgrade function to create a weak node reference to branch from the reference count node in branch. When we print the parent of leaf again, this time we'll get some variant holding branch. Now leaf can access its parent. When we print leaf, we also avoid the cycle of eventually ending in a stack overflow like we had in listing 15-26. The weak node references are printed as weak. The lack of infinite output indicates that this code didn't create a reference cycle. We can also tell this by looking at the values we get from calling reference count : strong underscore count and reference count : weak underscore count. Visualizing changes to strong underscore count and weak underscore count. Let's look at how the strong underscore count and weak underscore count values of the reference count node instances change by creating a new inner scope by moving the creation of branch into that scope. By doing so, we can see what happens when branch is created and then dropped when it goes out of scope. The modifications are shown in listing 15-29. Listing 15-29, creating branch in an inner scope and examining strong and weak reference counts. After leaf is created, its reference count node has a strong count of 1 and a weak count of 0 in the inner scope. We call branch and associate it with leaf, at which point when we print the counts, the reference count node in the branch will have a strong count of 1 and a weak count of 1. For leaf.parent pointing to branch with a weak node, when we print the counts in leaf, we'll see it will have a strong count of 2 because branch now has a clone of the reference count node of leaf stored in branch.children, but will still have a weak count of 0. When the inner scope ends, branch goes out of scope and the strong count of reference count node decreases to 0, so the node is dropped. The weak count of 1 from leaf.parent has no bearing on whether or not node is dropped, so we don't get any memory leaks. If we try to access the parent of leaf after the end of the scope, we'll get none again. At the end of the program, the reference count node in leaf has a strong count of 1 and a weak count of 0 because the variable leaf is now the only reference to the reference count node again. All of the logic that manages the counts and value dropping is built into reference count T and weak T and their implementations of the drop trait. By specifying that the relationship from a child to its parent should be a weak T reference in the definition of node, you're able to have parent nodes pointing to children nodes and vice versa without creating a reference cycle and memory leaks. Summary. This chapter covered how to use smart pointers to make different guarantees and trade-offs from those Rust makes by default with regular references. The box T type has a known size and points to data allocated on the heap. The reference count T type keeps track of the number of references to data on the heap so that data can have multiple owners. The reference cell T type with its interior mutability gives us a type that we can use when we need an immutable type but need to change an inner value of that type. It also enforces the borrowing rules at runtime instead of at compile time. Also discussed were the dereference and drop traits, which enable a lot of functionality of smart pointers. We explored reference cycles that can cause memory leaks and how to prevent them using weak T. If this chapter has piqued your interest and you want to implement your own smart pointers, check out the Rust-Nomicon for more useful information. Next, we'll talk about concurrency in Rust. You'll even learn about a few new smart pointers. That was the end of 15. Next, we will do chapter 16. This seemed to be a long one. Okay, so on to the next chapter.